Thanks so much for the introduction and the invitation. So I hope you can hear me well. Otherwise, just let me know. Yeah, so wonderful. So maybe a very brief check-in here. Who's working or who's using machine learning in their daily work? Please, hands up. Okay, that's a very good amount. And I assume that if I ask who's using Earth observation or remote sensing data, then there's even more people raising their hands. But please do so. Okay, great. So today I will talk about learning from global Earth observation data. And with learning, I mean machine learning, but hopefully also at some point we as humans might learn something from these analysis. So let's get right into it. So we might all have seen this picture before, right? I borrowed this from the European Space Agency, and I really like it because it shows how exciting it is to work in this domain right now. It's such a diverse amount of sensors that is already in space. So you see here the timeline. We are now in 2025, but there's even more sensors to come. So what is exciting is that there's up to date, only the Copernicus missions have collected 34 petabytes of data. So raw data, raw observations, and all this data needs to be analyzed to actually derive some information from it that is useful to solve the challenges that we are interested in. So today I will like to present two research projects that I'm involved in. So one that Tom already mentioned, I will talk about global canopy height mapping using Sentinel-2 and JEDI. And then I will also talk about a more recent project, which we call Earth. This is a more general representation learning project that is not focused on one specific task, but is very much in the spirit of these foundation model goals. Okay, let's get started. So why do we care so much about mapping the Earth's forests or vegetation? And that is clearly because they provide these important ecosystem services, right? So forests are very important for biodiversity. They store up to 70% of the species living on land, but they also capture carbon. And because of that, the UN has developed these strategic goals to increase and maintain carbon stocks globally. So with this, we obviously tackle these very grand challenges of our society, like avoiding biodiversity collapse and then also mitigating climate change, or at some point, yeah, adapting to it. So, but these goals are important, but how can we measure if we make progress to it? So for that, we need high resolution data, and that's how we come to like canopy height mapping, because that is one of the most important drivers or indicators to map biomass and carbon stock at large scales. Okay, so I really like this picture because it just illustrates how challenging it can be to collect field data, right? This is obviously not always scalable to many locations, so we are generally quite limited when it comes to on-the-ground field data. So how can we measure vegetation height today? I was trying to map out like the current technology. So on this horizontal axis, we see the suitability of directly measuring vegetation structure. And then on the y-axis, we see the scalability in terms of spatial coverage and temporal resolution. And of course, on the very right, we can start with airborne LiDAR or photogrammetry, which we all know either from UAVs or airplanes. This can give us more or less a direct measurement of canopy height and structure. And as we move to the left, we can go to spaceborne LiDAR, which is much more noisy than airborne measurements, but gives already better global coverage. And then in the end, we can also look at things like optical satellite images, which are obviously not directly designed to measure vegetation height or structure, but maybe they are still useful for this task. So the question is a bit, as we go to the left, how do we make use of this data for such a task? And the answer might be to think about estimation and not necessarily measuring. And that's where deep learning comes in as a tool, a toolbox that can help us to overcome limitations of like understanding how things relate to each other, how this data might relate to canopy height. And we just want to exploit this large amount of data in our modeling. So the idea of this project was to combine Sentinel-2 and JEDI. So Sentinel-2, you might all be familiar with it. I will very briefly go into it. But the overall goal was to get a dense canopy height estimate, ideally an estimate for every Sentinel-2 pixel. So this gives us a 10-meter grid on the ground. Okay, this very briefly, Sentinel-2 is an optical sensor. So there are 4 bands that come at 10-meter ground sampling distance, and then there's a few extra bands that have 20 and 60-meter resolution. And I mean, the great advantage of this sensor, it has global coverage, and we have a rather high revisit time, so up to 3 to 5 days. So this gives us even observations even in very frequently clouded areas. Okay, so this is JEDI. JEDI does not have its own satellite. It's mounted on the International Space Station and has the size of a fridge. And it shoots like 8 parallel laser beams to the Earth and basically measures following the ISS ground tracks. So every laser point returns a vertical profile measurement. So within a 25-meter footprint, which looks like this. So we get the first return at the canopy top, and then we also measure some within like understory structure, and then in the end we get a ground return. And once it's solved how to extract canopy top height from this, we get very good reference data. But still, this is just sparse data, and the big question is how can we combine it with Sentinel-2, and how can we model the uncertainty in these estimates? So how do we approach this? As I already mentioned, we would like to estimate canopy height, vegetation height from Sentinel-2. And we approach this by training a convolutional neural network, a rather basic CNN, to estimate the canopy height, illustrated here at the top as the mean. But we also wanted to estimate the uncertainty, which is illustrated here at the bottom as the variance. And now how does JEDI come in? JEDI comes in as training data. These are our estimation targets on the very right. And we have this sparse supervision. So to train a neural network, we all know we need a loss function. So we extend here a bit beyond the mean squared error. So instead of just minimizing the squared error between the estimate and the target, we also estimate this variance. So this is the Gaussian negative log likelihood. And ultimately, we also do not only train a single CNN, but we train a small ensemble of CNNs to then aggregate the outcome of these multiple measures. Okay. So one big challenge when it comes to estimating canopy height from optical sensors is what you see here. So as we go, so these are the residuals. Negative means the model underestimates the reference data. As we go from left to right, we increase the height of the vegetation, but you see that the model starts to underestimate these very tall trees. So this is a big problem when it comes to downstream tasks like biomass estimation, because the tall trees really store a lot of carbon. So if we underestimate those, we will definitely underestimate the carbon stocks. So we tried a few techniques to improve this performance. So the first was to tell the model actually, where is it on Earth? So we conditioned it on geographical coordinates. This helped a little bit. Second was playing with different objectives, different loss functions. So balancing the data and giving more weight to these very rare observations of tall trees. And then lastly, ensembling also helped quite a bit. So we see how these arrow bars are moving upwards, but it's still far from perfect. And ultimately, we got an RMSE of 6 meters. And although we made progress in the taller canopies, we also paid a price for it, which is the overall overestimation of lower canopy heights. But ultimately, we deployed this at global scale to get a canopy height for the year 2020. And this boiled down to processing around 160 terabytes of imagery, because we had to process multiple Sentinel-2 images per location because of cloud coverage. To get basically full cover, we need to aggregate multiple observations. And that's how we ended up with an annual estimate. And if we look at the corresponding uncertainty map, it looks like this. So we see that the uncertainty correlates quite a bit with canopy height itself. So the higher, the harder. But then there are also regions like, for instance, Alaska in north, which has rather low vegetation height, but rather high uncertainty. And here, the red lines, they indicate basically the coverage of the JEDI sensor. JEDI does not go beyond 51 degrees north and south. So there's no training data there. So as we extrapolate to these new regions, uncertainty might arise because of lack of training data as well. And then some regions might be just extremely cloudy. The input data might still be imperfect by using only 10 images. In these cases, we might have to actually use more images to get a better map product in the end. Okay, what can we do with it? So I already mentioned biomass and carbon stock estimation quite a bit. This is a use case where we tried this in Southeast Asia. And on the right, you see basically how above ground carbon density correlates quite well with these canopy height estimates. And then the map here shows a categorization applying several thresholds to get different carbon stock categories. Another application might be change analysis. So we took this model and ran it for 2 years here for California. So we ran it for 2019 and 2021. And if we subtract it, it looks like this. And the interesting fact is that this correlates quite well with the mapped extent of a wildfire that happened in August 2020. So, but there are still several limitations. And one issue with this map is that it's overly smooth. So it has a bunch of reasons why that might happen. So first of all, the JEDI footprint is 25 meters as illustrated on the right. So it's slightly bigger than the Sentinel-2 pixel. But you can imagine what we did in this training approach. We basically simulated if JEDI would be located at every 10-meter pixel. So it kind of acts as a smoothing operator. But on top of that, what is much more severe is that the first version of JEDI had quite some geolocation uncertainty. So the footprints were not precisely located, and that definitely smooths out the prediction. Luckily, JEDI version 2 is much better in geolocation. So redoing the whole exercise would actually improve the results quite a bit. Okay, so to wrap up the first part, yeah, Sentinel-2 is actually quite useful for canopy height, although it was not explicitly designed for it. And the key to this is actually end-to-end learning how to extract features from Sentinel-2 images using a lot of training data. So, and then there's a bunch of downstream applications. I've already mentioned it: temporal analysis, biodiversity applications, using canopy height to characterize habitats, and so on. So the data is out there. It's also on Google Earth Engine, but you can also download it locally and can maybe use it in your application. Okay, so I think I will directly, in the interest of time, move to the second part. So I will talk about a new project, which we call Earth. And the idea here is, okay, what if we work on a problem that does not have so much data? So back to this image, the main question is, why not just use supervised deep learning? Like, I have a new application, why can I not just do the same thing? And the answer is, yeah, data is limited. Your training data might be biased, and you cannot easily collect more training data by simply annotating optical images on the screen. So data collection, training data collection might just be very hard. So just to illustrate that this is actually a problem, so here are 3, let's say, state-of-the-art dataset collections on agricultural field boundaries, crop yield forecasting, carbon flux estimation. So what all these state-of-the-art data sets have in common is they are extremely biased towards only a few countries. They are not a systematic sample of the Earth. And this is a huge challenge for machine learning solutions. Okay, back to this image. There's a big opportunity in Earth observation data. I mean, we've already done it somehow in the first project, but the key is that we can align all this data automatically. All this data has a geotag, all this data has a timestamp, so we can automatically pair sensors and map products. And this is what we leverage in this project. So we created a new global pre-training data set by pairing 12 different modalities at around 1.2 million locations. That number comes from the ImageNet baseline, so that the data set would be comparable to an ImageNet pre-trained model. And we focus on Sentinel-2, but we collect data from like these 4 years, from 2017 until 2020. And we can group these modalities into 2 groups. So on the top, you see what we called pixel level modalities, where we get a value for every pixel of Sentinel-2. We use Sentinel-2, Sentinel-1, Amsterdam elevation model, the canopy height map, 2 land cover maps. But then we also use another group of modalities, which we call image level. These come at much coarser spatial resolution, so we only get a single value per extracted image patch. But here we included also things like climate data, precipitation, temperature. And then we also use the geolocation and the observation date as modalities to basically have a proxy for seasonality. Okay, this is how it looks like. If you look at one sample, this is in the desert. So if you look at the dense modalities here, it looks quite not too interesting. There's not much going on, but still, if we look at the image level modalities, these can still tell us something about what is in this optical image. But if we go to a more interesting area, like one of these wetlands, we see there's a lot of structure in all these different derived products or different sensor measurements. And this is what we want to leverage to learn how to extract features from optical images. Once we have such a global pre-training data set where we have paired multiple modalities, we cannot do a lot of things. We can try to ask many research questions, and people often use the term multimodal representation learning, but they mean different things. And here I just wanted to briefly clarify what I believe these different things mean. So one thing is called cross-modal. First approach, where we would like to train one model that can be used on different input modalities. So the model should be generalizing to different inputs. Another approach we could actually call multimodal, where the goal would be to combine different modalities in the input, also at test time. And lastly, we can talk about multitask learning, where we train a model that can specialize on a specific input sensor, but it should generalize to different downstream tasks, to different outputs. So these are all super interesting questions, but we mainly focused on the last one to begin with, and we wanted to figure out, how can we now learn good representations for Sentinel-2, making use of this training data set. So how do we evaluate if it actually works? So luckily, there is, for instance, GeoBench, which is a collection of existing machine learning remote sensing benchmarks that is slightly harmonized, so it's much easier to work with maybe. And so there are a few downstream tasks that we will test our model on, including land cover classification or this local climate zone classification, which is much more fine-grained in the land cover types. So this was the main research question we ask when experimenting. How do multimodal pretext tasks like impact representation and then ultimately the translation to new downstream tasks? So you might have seen this, these pictures, this masked autoencoder, where you can formulate a pretext task just using image data without using any additional modalities. And there's either the vision transformer approach, but then there's also a convolutional approach, this ConvNext v2, and this is what we use to experiment with. And the idea here is that we would take an image, we would mask out random patches of this image, and then train a model that creates a representation, so a feature representation of the image that is then useful to reconstruct the masked out patches. So from the visible patches, we would reconstruct the invisible patches. And it has been shown that this is a meaningful pre-training task, and we can learn useful features that generalize to new tasks. So we build on this. This is our baseline if we train it on Sentinel-2, but we extend this framework by predicting all these other modalities at the same time. So we add these additional so-called decoders on top of it, and they all share the same representation, so the same feature extractor. And by doing this, we hope that we will learn generalizable representation that later on will generalize to new tasks. Okay, here's some results. So what we actually care about these extreme cases where we have only very little training data, and in machine learning, you often call this few shot evaluation. So few shots to learn. And this is on 3 different downstream tasks. This is the ImageNet baseline. So what if we use 100%, 50%, 5%, or only 1% of the available training data to train this model and then evaluate? And some models really go down to 0% accuracy. Okay, so I mentioned our baseline, this MM-Earth. So this line is the masked autoencoder trained on Sentinel-2 images. So it's a domain-specific masked autoencoder. In some cases, this can help improve the results, but not drastically. And lastly, this is our multi-modal pre-training. That seems quite promising to improve in this case. Okay, so we compared at that time to dedicated Sentinel-2, like pre-trained models, and it compares favorably. Now there's a whole catalog of pre-trained models that we could compare to. But we were also asking this question, okay, how to sample the Earth? And we looked at 2 things. So first of all, how many locations would we need? So we checked briefly, do we actually need 1 million, or would 100,000 locations be enough? And here we see that from the second line to the third line, performance drops quite a bit. So it seems like, okay, we definitely need these 1 million, but we cannot yet answer if we need more than that. And then lastly, we also looked at how big should these image patches actually be? So we extracted originally like 128 by 128 pixel patches, but then we experimented with 64 by 64 pixel patches. This reduces the data volume drastically, speeds up the training process, experimentation drastically. But the good thing is it does not reduce performance. So for this particular pre-training strategy, actually, the context of 64 by 64 pixels was enough to learn meaningful features for these downstream tasks. It might change if you experiment with another pretext task. Okay, so I need to speed up a bit. I have 3 minutes left. So this is one thing I wanted to show today, because friends from ESA and this Asterisk Labs, they took our model and ran it globally. They also took a bunch of other well-known, like more general computer vision models and ran it globally on the Major Tom archive or sample from Sentinel-2. And this is how it looks like if you visualize the first 3 principal components. We see that these features start to cluster geographically quite a bit. So these are now pre-computed and available to use. And of course, now we all heard about the Google embeddings. So that's quite interesting to see momentum also in the big tech companies creating such embeddings and make them available. Okay, so as I mentioned, multimodal learning is actually quite interesting, because what we would want to do is reduce ambiguity in these estimates. We all agree, I guess, that optical images, this cannot be enough to estimate biomass. Obviously, there's a huge uncertainty. So by adding more data like Sentinel-1, temperature, etc., we hope that at some point we can reduce the ambiguity and improve these uncertainty estimates. So this is a thing that Lucia, a PhD student from Harvard that I'm working with, is working on. It's work in progress, but we are building now a follow-up like MMEarth bench, where we would like to actually test exactly that. So she's building a new downstream task for biomass, species, range estimation, and some soil parameters to basically check, oh, is this multimodal input data actually used in the dedicated multimodal representation learning models? And can we make progress there? And before I conclude, a little bit of advertisement for a new research network that we started, or colleagues in Sweden at RISE have started this end of last year. So we call it Climate AI Nordics, and you're all welcome to join. It has a focus on the Nordic countries, but we already have more than 50 international affiliates. So our goal is to also organize workshops, events. We have a Slack channel, we have some newsletter. So it's to build, the idea is to build a community, find like-minded people, and yeah. So please have a look and join if you feel like. So with this, I would like to conclude. And yeah, I'm sticking around the whole week. So if you would like to have a one-on-one chat, please reach out. If you cannot find me here, send me an email and we will arrange something. Thanks so much.